Okay, so let's quickly put all these things together, back together to derive the whole equations as we said. This is where we stopped, so let's start here. So now we have the F equal ma equations. M is unit mass. We are carrying density here, so that's per unit mass. So du dt, the zonal momentum equation or zonal equation of motion, is the pressure gradient minus 1 over rho dp dx. We are still carrying rho, even though it's incompressible. We cannot throw it out because it becomes very important in the vertical, where gravity and density together decide the net buoyancy, plus Fv, the Coriolis term, plus the eddy viscosity or eddy momentum term in the horizontal, momentum mixing term in the horizontal, momentum viscosity term in the horizontal. The vertical term we have reduced from the wind stress forcing to the vertical eddy viscosity and the vertical shear del squared u del z squared equation. And we have the advection equation minus advection terms minus u du dx minus v du dy minus w du dz. Okay, so similarly in the meridional direction we have dv dt equal to the pressure gradient term, Coriolis term, eddy momentum flux terms, eddy, you can think of eddy viscosity term for momentum mixing, and the momentum advection terms, and those are the terms that are written here as A, B, C, D to H. In the vertical, we can still write dw dt equal minus 1 over rho dp dz minus g, which is the gravitational pull, and the momentum advection in the vertical. But as we said, most often, almost always in fact, we end up making the hydrostatic assumption, which means the vertical pressure gradient term is balanced by gravity, and W is typically very tiny, so using order of magnitude analysis we can drop W, so dw dt and the vertical advection of vertical momentum can be dropped, so then we just end up writing dp dz equal to minus rho g, as we will see later on. And of course we still have the continuity equation, where we now use the incompressibility approximation to write du dx plus dv dy plus dw dz equal to 0. I have these derived, if you want full derivation, elsewhere in my dynamics course that you can look up. For our purposes here, this should be enough. So you can then take the full governing equations and make several simplifying assumptions. If you have steady inviscid flow, then you can set du dt equal to 0 because it's a steady flow. Inviscid means these terms go to 0, and if there are certain situations where the inertial acceleration is much more dominant than, planetary acceleration term, which is the Coriolis term, is much more dominant than the inertial acceleration terms or the momentum advection terms plus the acceleration term, then you get just a balance between Coriolis and pressure gradient in both zonal and meridional directions. So as we had seen before, we end up with what we call geostrophy, where pressure gradient balances the momentum terms. Okay, so in this case obviously it's just Coriolis force versus pressure gradient. So Coriolis force is balancing the pressure gradient. The cutest thing that happens, of course we can write this as 1 over rho dp dx equal Fv as we did before, and 1 over rho dp dy is minus F times u. And the cutest thing that comes out of this is that the flow is not along pressure gradient, but actually in full geostrophic balance, currents will be along constant pressure lines. Okay, so pressure lines which is very counterintuitive, because you expect flow to be down the pressure gradient, but if pressure gradient can be balanced by Coriolis, then flow tends to be along constant pressure lines. Okay, so geostrophy can be written as V geostrophic equal to 1 over rho f dp dx, and U geostrophic is minus 1 over rho f dp dy. And of course in the vertical we have the geostrophic balance 1 over rho dp dz equal to minus g, and we can write that as dp dz equal to minus rho g. How do we, so this is saying that the pressure at any depth is just equal to weight of the water above plus the pressure, the sea level pressure. So how can pressure change horizontally if the pressure just depends on depth? Well, it turns out that in the ocean you also have sea level changes. So if you look in the x or y direction, the free surface of the ocean is going to be lower than the long-term average in some places and higher in some places. So then pressure is not just rho g times the depth. It will also depend on how the sea surface is higher in some place and lower in some place, which means there will be horizontal pressure gradients. So if you consider 3 points A, B and C, which is at x1 at z0 and x2 at z0, so longitudinal positions are different but the depths are the same, but the amount of water on top of x1 or A is different than here, and C of course is at the zero sea level, relatively speaking. So schematic diagram of a sloping sea surface here relative to a geoid dashed black line, which is the constant gravity surface, which is hypothetical surface because you have mountains in the ocean, cavities, or what do you call them, abysses in the ocean, and those create water columns that are of dramatically different depths, and as the planet is rotating there is a dynamic balance, so the geoid is not a flat surface, right? Imagine a cup of water. If it is just sitting there, the surface is flat, but if you take a spoon and spin it, then you're going to have surface variations in the cup of water you have, right? So this illustrates the horizontal gradients in sea surface height give rise to and are sufficient to characterize horizontal pressure gradients in the ocean. So in a first order sense, you can also think that the sea level height gradients are going to be related to the pressure gradients in the x and y directions, hence they are going to be related to the geostrophic currents in the ocean as well. And that's what we are saying here. Meridional geostrophic current is going to be G divided by F times d eta dx. So the sea surface gradient in the x direction is going to give us meridional geostrophic current, and the meridional sea surface gradient is going to give us zonal geostrophic current. And you can see that here. Sea surface height above the geoid eta average from 1993 to 2010 from Aviso satellite altimeter product. Altimeter is basically flying up there at some 1400 kilometers. It is sending a laser down and measuring the distance, travel distance, to see how the travel distance changes based on the sea surface height change. So it can detect changes at the level of 1 centimeter sitting high up in the atmosphere by looking at the travel time change, and it tells us that where there were cold temperatures, sea level is lower relative to the reference geoid, and in the subtropical gyre where currents converge and thermocline is pushed down, warm waters pile up, sea surface height is larger. So if you go from the equator to the center of the subtropical gyre, sea level rises by about 2 meters. If you go from the east to west, sea level rises by about 50 centimeters here in the Pacific. So you can see the dynamic features of how sea level is high and low depending on how the dynamics of the circulation works, and you can use these d eta dx and d eta dy to compute geostrophic currents that you can see are seen here as vectors. So you can see the sea surface height here. So let's read the caption. Sea surface height above the geoid eta averaged from 1993 to 2010, again as we said before, with contour interval of 0.2 meters here and values spanning roughly minus 1.5 meters to 1.5 meters. Here, closer view of eta and calculated geostrophic velocity vectors in the North Atlantic region, looking at the Gulf Stream, subtropical gyre, and the subpolar gyre. So you have clockwise flow here and counterclockwise flow here. So if you use your Coriolis, is pushed to the right of the direction of motion, so you have converging waters into the middle here, and you have diverging waters out of the middle here. So spanning roughly minus 0.6 to minus 0.9 meters here. This is the longitudinal profile of sea level and geostrophic currents along 36.5 north, which is somewhere here. So you can see that the sea level is low here and increases towards this direction and then falls off as you go towards the east with respect to the zonal mean. So corresponding to that, you have high geostrophic, the d eta dx is very large, so v is very large, and d eta dx gets flat, so v becomes small, and so on and so forth. So you can see the close relation between sea level gradient, pressure gradient, and geostrophic currents. So this is near surface currents in 2012 as calculated by applying geostrophic velocity equations to observed sea surface height. In A as estimated from Oscar satellite product, and B, A is the observed sea surface height, Oscar geostrophic currents, and the so this is directly estimated from sea surface height. This is estimated by Oscar, which is a product, and this is their difference. And you can see the differences can be significant, a significant fraction of the actual currents. Okay, large scale features are captured well, but you can see that the differences are not small at all. So these kind of errors do matters, especially because when we consider advection of heat and salt and how the atmosphere is affected by the heat and salt, obviously these errors are important. But nonetheless, we can estimate currents using observations of winds and sea surface heights. In fact, some of the differences here are related to the contribution from the winds to the geostrophic currents. So the total currents are not just geostrophic, they are geostrophic plus wind driven. Okay, remember, geostrophic is just related to sea level pressure gradient, sea level height gradient, and pressure gradient, whereas wind currents are friction driven currents. In the geostrophic balance, there is no friction. We are just balancing Coriolis term to the pressure gradient term. Okay, so just remember that.